want to take a brief minute to append what we learned in the last video and talk about general rate laws. In our discussion of the last video, we were really concerned with reactions that had a single reactant, and what I want to do is generalize that. So our learning goals are to define the rate of reaction that has multiple reactants, which is actually the more common case. So when we have multiple reactants, let's say we have a reaction like acetylene reacting with hydrogen to form ethane, how would we treat the rate law in this case? How would we write it? We could use either the acetylene, C2H2, or hydrogen to do that. So if, for example, I was going to write it in terms of the acetylene disappearance, I might write a rate law that looks something like this, where the rate is equal to the disappearance, negative change in acetylene concentration per time. And if I don't specify any numbers here, I'm just going to say that that change in the acetylene concentration might be some number x, so it would be minus x over delta t. Now, how would that compare to the rate of H2 disappearance? Well, in this case, as I see H2 disappear, it will disappear twice as fast. So there's a relationship between those two rates, and I have to pay attention to the fact that there is that relationship between them. H2 is going to disappear twice as fast as acetylene. We saw this in the time evolution curve in the previous video. The slope depended upon the stoichiometric ratio of the two species. So in this case, there's two H2s disappearing every time one acetylene disappears, so its rate will be twice as steep. So now if we want to define an overall rate, and we've got to choose between these, since they're related to one another, we can make a consistent definition for rate that takes into account the stoichiometric ratio. So I'm going to propose that we do it this way, that we might write it as the rate of disappearance of the acetylene, but that's equal to a half the rate of the disappearance of H2. So in other words, our rate then will be formally defined as the rate of disappearance of the acetylene. Now, I've also written at the very end another possibility, and that is we could write the rate as the rate of appearance of the product ethane in this case. It's not very common that we do this. We usually focus on the reactants because once products are formed, other things can happen, and so it's really not indicative of the rate of a particular reaction. The rate of a reaction seems more tied to the disappearance of the reactants, so that's why we focus on that. So now if we were to look back at our reaction of N2O4, we might write a rate that looks like this, where it's the rate of disappearance, so negative the change in the concentration of N2O4 with respect to time, but that would be equal to the positive change in NO2 with respect to time divided by 2. We've added the 2 now, which is the stoichiometric coefficient. So this leads us in the direction of a general rate law. So I want you to consider a very abstract reaction of A plus B going to products. And now when we write the rate law, instead of just including one of those, we need to include them both. We need to include a term that is proportional to the concentration of A and a term that's proportional to the concentration of B. Now, in general, we're going to have each of those raised to some power, and the total power is going to be the order of the reaction. So in other words, whenever you're asked what is the total order of a reaction that involves more than one reactant, you have to add the exponent that go with each of the reactants that appear in the rate law. So in this case, that order would be M plus N. That would be our order. Now let's look at an example. If I consider, for example, the synthesis of ammonia, the rate in this case is going to depend both on the concentration of the nitrogen and the concentration of the hydrogen, and they'll be raised to different powers typically. It can happen that they're raised to the same power, but it should be more general that they're raised to different powers. I should say that the rate law in these cases, we almost never write it as depending upon the products. So we're focusing on the reactants. The rate law is going to be equal to a constant times the concentrations of the reactants raised to different powers. Now, you might ask, are the exponents of the rate law related to the coefficients in the balanced equation? Well, unfortunately, the answer is sometimes, but not always, so you can't count on that. In fact, it turns out that those exponents are things that we have to learn by doing a direct experiment and finding out what nature tells us those exponents should be. It's not something that we can predict a priori from the balanced chemical equation.